Okay, we're back. We're going to see what you guys think. How big is the biggest dice? Well, let's find out. What did you say? Okay, 21 people were very bold and said 100. And then we have a range, a nice distribution. This is almost like a geometric distribution. Starts out very low, and they're getting smaller every time. So let's see what it is. And hopefully this dock cam will not fail me. So switch to the dock cam. And then hopefully I also didn't forget them in my office. That would be the real shame. Okay, here are the dice. So the first dice we have, this is the beautiful. How many sides is this dice? Well, there's a 10. Okay, 10, 8. Oh, it goes all the way up to 12. This is a 12-sided dice. Beautiful. 12-sided dice. What else we got? Here's one you might have seen before. This is everyone's favorite 20-sided dice, the dodecahedron. All right, 20. Find the maximum. Everybody knows that from D&D. Okay, but then it gets even more crazy. We have these next two are getting even more crazy. This one I think is 24. 24. This one goes all the way up to also 24. 20. Oh, I see a 30. A 30. 30. I think it's a 30-sided dice. But then we have the Big Daddy, the biggest of them all. Look at this. This is basically a golf ball. Look at this. How many sides does this one have? 55. Let's look for the biggest number. 55. 59. I think there's a 60 on here somewhere. Where's the 60 hiding? What a disaster. Okay.
It's been stolen.
Stolen. Maybe it goes 0 to 60 instead of 1 to...
If you see the one, it's probably on the opposite side.
Oh, that's a good idea. Okay. 1. Aha! Yes, that worked. Amazing. This one is basically a golf ball. Like when you roll this one, it rolls forever. It doesn't stop. So 60-sided, very impressive. That's a big dice. But that's not the biggest one. This is the biggest one. Look at this bad boy. 100. This one is truly a sphere. And those are my dice that I bought for this class. I'm going to expense them. So thank you for letting me teach the class. What are we doing today is we're trying to say, look, we've done problems with 6-sided dice and stuff. If you have a 100-sided dice, there's actually simple things you can do. So a 100-sided dice seems way more complicated than these ones, but you can approximate it very well by something very simple. And that's what we're going to learn about today. So we're going to look at what happens as you make the number of sides bigger and bigger. We're going to go start here and move our way up. And you can imagine we're going to go all the way to infinity. So this is 100. We're going to go up to 200. There's actually one point in this class we've already used a dice with 365 sides. And that was the very first day of class, where we said the birthday problem, there's 365 days in a year, and I was pretending each of you guys was a 365-sided dice. What day is your birthday? And we did a problem with that. And so we're going to learn about this kind of stuff today. Maybe, I'll pass this around. You guys can play with the 100-sided dice. So feel free to marvel at the glory of the 100-sided dice as it comes around the classroom. Okay. Let me try to quickly fix this video problem over here. Okay. All right. So what do I want to do? I want to start with asking questions. What happens to a dice roll as you add more and more sides? And very specifically, I have a specific question I want to answer. And I'm going to put up the question, but I'm not going to let you answer it yet because I want to show you some pictures first. So here's the problem. Let me also put it over here on the HDMI. So let dn, D stands for dice, n is the number of sides. So dn is a random variable for a dice roll with n sides. Depending on how much other times you've seen sequences in calculus and that kind of thing, this might scare you or it might not. But every other class we've had one random variable, like x is this, g is this. In this class we have a whole sequence of random variables. There's D1, a one-sided dice, D2, D3, D4, and so on. And we're looking at Dn and asking what happens to Dn when n is getting bigger and bigger. And the first question is, what is the probability that Dn equals 7? Dn equals 7. And I'm going to show you a picture of what this looks like in my favorite graphing calculator program, Desmos. Okay? And in Desmos, I have it set up. Can I make this a little bit bigger? Let's see. All right, here we go. how do I represent a dice roll in Desmos? I have represented the outcomes of the dice roll as these big blobs. So each of these blobs represents the outcomes of a dice roll. Right now I have n equals 6. It's a 6-sided dice. There are 6 equally sized blobs. They live at 1, 2, 3, 4, 5, 6. Those are the outcomes that a dice can take. And now if I zoom out a bit, we can see what happens when you add more and more. So those are my 6 blobs. If you start making n bigger, and it should go up by 1s, let's do it. Let's animate it slowly. If you start making n bigger, you get more blobs. Okay, there we go. So now we're up to 13. Let's stop at 20. That's a good number. 17, 18, 19, 20. Okay, back it off by 1. So this is the D&D dice. The 20-sided dice has 20 equally sized blobs. Maybe I can make the blobs a little more round for your convenience. So 20 blobs. Okay, they're little tiny blobs. And as you go, you can make this bigger and bigger and bigger. And the size of the blobs is supposed to represent their probabilities. So you see when there's only 1, it's a 100% chance. With 2, they're shrinking down, and the blobs sort of get smaller as you add more and more. So hopefully that picture makes sense. I don't know how I can zoom in to make it. It's hard to make it zoom in on one axis and not the other axis. So we're kind of stuck with the picture we have. Okay, I'll hit play. There's our blobs. Any questions or comments about what's being shown here, how this thing works? So I'm representing the dice roll as blobs that represent the probabilities. Okay, if there's no questions, then you guys should have no problem doing the mathematize, which says, as n gets large, what's the probability dn equals 7? So dn equals 7 was somewhere on that page, and it's getting closer and closer to what? And then there's a true or false. I can replace 7 with any fixed value of x. So the 7 is not a special 7, or is it? I don't know. You tell me. How does it change if you change 7 with something else? Okay, I'll give you a minute to think. Feel free to discuss with your neighbors as we go. Yes.
Did you purposely not specify that the value of x has to be in the range of
Yeah.
Okay.
Yes, it doesn't matter. Yeah, that's right. Okay. Okay, time is up. Let us see what you guys said. As n gets large, the probability that the dice equals 7, that's the probability you roll the dice, and it comes out to 7. But we're thinking of the dice getting bigger and bigger. So you start with the 12-sided dice, then you move to the 20-sided dice, then the 24, then the 30, then the 60, then the 100-sided dice. And you're saying, as a sequence of numbers, what is this sequence of numbers doing? And it's getting closer and closer to what? You guys said what? Getting closer and closer to 52 out of 58 people. Notice the answer is 0. 0. And that is the correct answer. So this is the first observation. The probability is getting closer and closer to 0. The next question is does it matter if you replace 7 with x? And the answer is true. How many people got it right? 90% of people. So very good, very observant. If you look at individual probabilities, they're getting closer to 0. And you can kind of see that in my picture. Even though the blobs start out big, they shrink over time, and they kind of effervesce and disappear. So as you add more and more sides, the probability of any individual point is shrinking away down to nothing, and you got nothing left over. Let me point out one thing. This was a great question that Gary asked. Let me point out this one thing. So a lot of people think that the probability that dn equals x, some people will write that this is 1 over n. And then they'll say 1 over n is a sequence as n gets big. You have 1 divided by a huge number. It's getting closer and closer to 0. And that is almost exactly correct. It's morally true, but you're missing one thing, which is it's only 1 over n if x is bigger than n. Otherwise, it's 0 if x is less than n. So if I roll a 12-sided dice and say, what's the probability it's 100, then the probability is going to be 0. It only kicks into 1 over n as soon as you cross x is bigger than n. But this happens eventually. So eventually it's 1 over n, and then eventually the 1 over n goes down to 0. So the probabilities, they are 0 for a while as a sequence of numbers. As a sequence of numbers. So this sequence of numbers, the probabilities, it's 0, 0, 0, 0, 0. Then all of a sudden it jumps up to like 1 over n, and then it starts to shrink down to 0. So as a sequence of numbers, it's getting closer and closer to 0 as you go to infinity. If you've taken calculus, you no doubt recognize this as a limit. We're saying the limit is 0, but for us, saying it's getting close to 0 is enough. Questions about that one? Yeah, over here, yeah.
Should it be x is less than n? Because n is the maximum number on the die, so it has to be under.
Do I have it backwards? Yes, I have it backwards. Thank you. Very good. Okay. All right. Hopefully, when I said it out loud in words, I said it correctly. X is less than n if x is bigger than n.
And it could also be the maximum on the die, so
there we go.
less than or equal to.
Yes, or equal to. Thank you. Very good. Less than or equal to. Yeah. So, and our dice rolls are something. They start at 1, and they end at n. This is an important thing that I kind of did without saying. By the way, this is called the discrete uniform random variable on the set 1 to n. So the discrete uniform random variable for any set picks all of them with equal probability. If your numbers are 1, 2, 3, all the way up to n, that's dn. Okay, great. I think this one we have sorted out. Okay, next question. Okay, the chance it's equal to something is going to 0. What about the chance that it's less than something? That's what we call the cumulative probability. That is part 2. Part 2 today is the chance that it's less than something. Okay. dn is a dice roll for a dice with n signs. Figure out what happens to the cumulative distribution function fn of 7. That's the probability dn is less than 7. What is that getting closer and closer to? And then, same true false as before. What happens if you replace the 7 with a different x? Okay, I'll let you think what happens here. And if you can figure it out, great. Okay, there's like 10 seconds left. 40 people have answered. I think there's like 10 or 15 people left to go. Put in your final guesses. What happens to the cumulative distribution function? What is that converging to? Okay, and it's beeping, but you can't hear it. Okay, that's fine. Let's look at the answers. Okay, before we had a very strong majority on 0. It's like 50 plus people. Now only 31 people say 0. 14 people say 1. Some people say 7. Some people say a half. Some people say does not get close to any number. Okay. And did people say true or false over here? And here we have 42 to 13 split. So not as confident as we were before. Let's take a look at what's going on in the Desmos. So in addition to the individual blobs, I have also plotted the cumulative distribution function. And the cumulative distribution function is something we've seen now. It's a function that always has y values between 0 and 1. It's the probability that you're less than something. And I've plotted it over here in blue. So here is the cumulative distribution function for a dice roll. Okay? So what is the chance you're less than or equal to 1? It's definitely 0%. You're always less than 1 on the dice roll. What is the chance you're less than 2? Well, you have to roll a 1. So the probability here jumps up by 1/10. And do I have n equals 10 right now? Great. So this is a 10-sided dice. The chance of getting less than 2 is 1. The chance of getting less than 3 is 2/10. The chance of getting less than 4 is 3/10, and so on. So it's this nice step function. If you're careful with the equal sign, you will fill in the circle on the right side. I wasn't careful with that. So it's this step function, and that is the CDF of a dice roll, the cumulative distribution function for a dice roll. So let's write this down. This is worth writing down. The CDF, that's F. I'm going to call it Fn because it depends on x. It's the probability that dn is less than x. Gary, do we normally do less than x or less than or equal to x?
Less than or equal.
We normally do less than or equal to. I was pretty sure we do less than or equal to.
And
So
a capital F.
and we do a capital F if you're. See, us mathematicians, everything is just a function.
Any way you define it.
Yeah. Okay, so it's less than or equal to, which means let's figure out where should the sides of the function be. So it's a staircase function, and if it's less than or equal to, then it should include 1 and have a hole here at 0. So as soon as x equals 1, the probability is 1/10. If you're at, what's the chance it's less than or equal to 0.999, then it's 0. So it's a function, it's a staircase function with holes on the right. Is a staircase. And it looks like this. So it goes whoop, and then boop, and then boop. Beautiful, beautiful, beautiful little thing. Okay. And the number of steps here, eventually it hits 1. So here it hits 1. It hits 1 exactly at x equals n. And here is x equals 1 at the very first value. So there's what the staircase function looks like. And these holes are filled in correctly to make this less than or equal to work. That is the cumulative distribution function. By the way, while I'm here, I cannot resist telling you the name of such functions. There's a name for functions that have their holes set up this way, where they're filled in from this side and they have a hole over here. You're not going to believe the name of this thing. It is called a CAD-LAG function. CAD-LAG. I'll give you a free coffee if you can figure out does anyone know what CAD-LAG stands for? It's an acronym. CAD-LAG. It stands for Continue à droite et limite à gauche. It's a French acronym, and it means that the function is continuous from this way, but has a limit from this way. So the holes, it has to have a non-filled-in hole on one side and it has to have a filled-in hole on the other side. Okay, CAD-LAG. I believe there's an accent in it, CAD-LAG like that. Did you know about CAD-LAG, Gary?
I did not.
Okay, now you're learning.
The full name, could you write that one out?
Yeah, continue, well, I can't, if you thought my spelling in English was bad, then continue
I was just testing.
à droite et limite à gauche. So continuous from the right and has a limit from the left. There's a Wikipedia page on CAD-LAG. Okay, so the CDF is always CAD-LAG, and it looks like this for the staircase. Okay, what are we trying to say? We're trying to see what happens when d gets large, or n gets large. So I'm just going to start sliding the n value. Let's do it in super slow-mo. 0.05 speed, the slowest, and we're just going to start to crank up the n value and see where does this function go. What does it do? So here it is. It's always a staircase. The number of stairs is increasing, and how far out it goes is also increasing. Okay, I got to zoom out a bit now. Let's zoom out a bit. So there's my function. Let's speed it up a bit. This is a little bit too slow. Where is that function going? What's going to happen as n gets larger and larger? So in particular, we wanted the value at 7. So 7 is like here. What is happening to the value of the function at x equals 7? That's the probability that dn is less than 7. It's here, and as you go out, it's going down, down, down. Let me make it even larger. Let's go up to 1,000. And let's make it faster. There we go. So here at x equals 7, it started out as a pretty reasonable probability, but as n increases, this whole function just is getting flat. It's getting a nice flat function, and in fact, it's shrinking down to 0. Okay, here we're up in the 700s. It doesn't look like much. It kind of slows down as you go. But if you wait long enough, it kind of gets flat enough everywhere. So what is the correct answer? Most people figured it out. The answer is 0. Is 0, okay. Is 0. So that's good. And what happens if you replace 7 with x? What if you're not at 7, but you're at some arbitrary place? You start over here at 40. Okay, it takes longer to get down to 0, but eventually this whole function is just collapsing away down to 0. This function goes to 0 everywhere on the x-axis. So the answer is true. True. And most people got that right. So the dice roll, the probabilities go to 0, and the cumulative distribution function goes to 0. So the observation, the CDF fn of x equals the probability that xn dn, keep calling it x, dn is less than or equal to x. This goes to 0. Goes to 0 as n goes to infinity. So as n is getting bigger and bigger, this whole thing goes to 0. Okay, now we're in a bit of a pickle here, because we want to say what happens to these dice as n goes to infinity, and basically the two things we've looked at so far, it looks like the dice just vanish. All the probabilities go to 0, the cumulative distribution function goes to 0. Like you could write down that fn of x converges to the function 0, the 0 function, the function that's always 0. And you could say, okay, is 0 the cumulative distribution function of anything? Like, no, it's not. This is the probabilities are always 0. This is the silliest thing in the world. So we have a problem here. Things are sort of escaping away to infinity. This is when mathematicians see this kind of picture, we think of, oh, things are vanishing at infinity. The mass of this function is leaving at positive infinity. It's running away to infinity, and in the limit, it escapes the x-axis. So that's quite annoying. So what we need is an idea to try to wrangle this thing and contain it inside some smaller interval. And that's my next question for you. Let's brainstorm. How are we going to contain this function? How are we going to contain it? Hopefully that's what I have. The dice roll seems to spread out and disappear as n gets larger and larger. So as a random variable, it's sort of disappearing in some sense. Do you have any ideas on how we could contain the dice roll in some way so it does get close to something? And a related idea is, just imagine you were trying to approximate this dice roll. How would you approximate it? What we've said is like the values themselves can't be approximated, but maybe something else can be approximated. All right, I'll let you guys think for a bit. Feel free to brainstorm and talk to your neighbors. Try to figure out what this is. Of course, there's no right or wrong answer. This is just what you think, and then I'll tell you the idea that mathematicians came up with that they used. All right, I'll tell you that in 2 minutes. Okay, there's like 30 seconds left. Put in your guesses. If you really have no idea, put in a IDK. Let me know. I have one other question for you guys. Where did my dice end up? Who's got the dice? Okay, I'll come grab it from you right now. Okay, time is up. Let us see if you came up with the idea to contain these probabilities and bend them to our will. What do you do to bend them to your will? Let's see. Ooh, okay. I don't know is the biggest one. We got interval. Interval. Let's see. What else? I don't know. These are great. Expected value of x will give you a hint on what to do. So the expected value of x is just a number. It won't tell you what to do. But if you calculate the expected value, you will find it is n plus 1 divided by 2. So the expected value of this random variable is like n is getting bigger and bigger. That tells you maybe we've got to do something to make sure the expected value doesn't explode to infinity. Okay. All right. Placing an upper bound. So you could stop. You just stop, man. Cool it. No, that's not what we do. That's never what we do. Use limits. So this is exactly what we want to do. We want to use limits. And on its own, it doesn't converge to something. We have to do something to it. Rig it. Yeah, that's a good one. Infinite sums. Add a restriction. No. Okay. One. Yeah. Woo. This is a lot of ones. Okay. The number of ones goes to infinity. Okay. Bound. Okay. Ignore the sigma as an interval. I want to see if anybody figured it out. Don't know. Limit. Number 33. Divide the roll by n. Divide the roll by n. So the dice on its own is vanishing, is spreading out, and doesn't do anything nice. But what happens if we divide the roll by n? That is saying, when you roll the 100-sided dice, don't tell me the number you got. Tell me how far, what fraction of the maximum value did you get, right? If you roll a 73, instead of saying 73, you should say 0.73. You got a 73% of the highest value. And by doing that, we can compare the 100-sided dice to the 60-sided dice, right? By looking of them as percentages. And that is exactly the same as dividing by n and mapping the results to 0, 1. That is exactly the idea we're going to use. So here is the idea, the light bulb moment. dn goes away. dn is bad. Or let's say it doesn't converge, has no limit. Has no limit. But what about dn divided by n? And this is a new random variable. This is the beautiful thing about random variables. We can call this xn. So xn is dn divided by n. And we can ask, what is going on with xn as the number of sides goes to infinity? And this is, again, this is like you roll a dice, and you don't look at the raw value. You look at the fraction of the number of sides you got. So if you get the highest possible number, then xn equals 1. If you get the middle number, then xn equals like a half. And the point is, this is always in 0 to 1. So it's some random variable. It's always in 0, 1. We're going to call it xn. And let's see what we can say about xn. And again, I'm going to do it with Desmos. So I have the same situation as before. Let me make the n's a bit more reasonable. 100. And OK, here's our thing. There's our blobs. I'm going to plot the same thing, the blobs and the cumulative distribution function, but not for the d's, but for the x's. And here's what it looks like. So the blobs, let's do the blobs first. The blobs look like this. Oh, you can barely see them. That's because all the blobs are in 0, 1, right? We said the random variable is always 0, 1 value. So we better zoom into 0, 1. OK, zoom into these blobs. There's all the blobs. OK, that's a lot of blobs. What is this right now? 32. Let's make it 6. All right, 6 blobs. So if you roll a 6-sided dice, you either get 100%, or a sixth, or 2/6, or a half, right? Something between 0 and 1. And as you add more blobs, all the blobs get smaller, right? The probability of each one, it's the same exact sizes as before, but they kind of moosh together and spread out over the interval 0, 1. Very nice. This is a lot better than before. Before they were just like vanishing, and now each individual point vanishes, but like in aggregate, they seem to be doing something. Okay, cool. All right, that's cool. What else can I look at? The CDF, the cumulative distribution function. That's this function g. And g is, again, it's a staircase function, just like before, the cumulative distribution for xn. But what happens as n goes to infinity? Let's see. So as you add more staircases, it's always ending at 1. We've constrained the random variable to always live between 0 and 1. So as you add more staircases, they get more and more dense here in the middle. And now it's not going to 0. Before it was flattening down to 0. Now it's not going to 0. It's converging to a very nice function. And that function is the function y equals x. Let's turn that on. This purple function. So this function is 0 if x is less than 0. It's y equals x between 0 and 1. And it is 1 outside of this. So what is the moral of the story? By dividing by n, we did get a nice limit. Okay, so the probability of xn equals any value, that's the probability that dn over n equals any value. This is still vanishes. Those are the individual probabilities, the sizes of those blobs. But the CDF is converging. The probability that xn is less than or equal to x, that is the probability that dn over n is less than or equal to x. This one is a staircase, and it gets closer and closer to this function, 0, x, or 1, if x is less than 0, if x is bigger than 0, or if x is between 0 and 1. So the CDF, I guess you would call this Fn. So Gary, what do you statisticians do now? Because Fn is already taken. I already named Fn with the D's. Now I got the X's.
We go to G's.
G's, okay. G's, capital G, Gn of x. So the CDF is converging. And this guy, this is the CDF of a legitimate random variable. This is the CDF of something. So it's somebody whose cumulative distribution function is this straight line. That's the purple line. So the green are the dice rolls, and the dice rolls, as you add more and more sides, if you make sure to divide by n, it's getting closer and closer to this purple guy. And the purple guy is the CDF of something. Does anyone know what it is the CDF of? What random variable has a CDF that looks like that? Let's see. We can ask questions. What's the this purple random variable, whatever it is, what's the probability that it's less than a half? Well, we plug in a half and we get a half. So it's a random variable where the chance of it being less than a half is a half. All right, good. What's the chance of it being less than 0.9? Well, you plug in 0.9. The chance of it being less than 0.9 is also 0.9. So this random variable, the chances of it being less than 0.9 are 0.9. The chances of it being less than a half are a half. The chance of it being less than a quarter is a quarter. Yeah. It's a uniform distribution. This is the CDF of a uniform distribution. And I think we called this one the UNIF 0, 1. So it's uniform between 0 and 1. It has an equal chance, sort of being any number between 0 and 1. And of course, this was all slippery. We couldn't figure out what it is. It has no chance of being any individual point, but it has a CDF that we got with areas. And so what we have shown that dn over n, the dice roll divided by the number of sides, it is converging to a uniform 0, 1. And this particular type of convergence is called convergence in distribution. Convergence in distribution. And this is the best part of the whole bit. Mathematicians have a special arrow they use just for this, and it's a double arrow. If you do a double arrow like that in probability, that means convergence in distribution. And what it means is exactly what we saw. The cumulative distribution functions converge. And this is very useful because what this tells you, if you have a dice, dn over n is approximately a uniform. So anytime you want to calculate something about a dice roll with 100 sides, don't bother with the dice, just replace it with the uniform, and you can do anything you want. Yeah?
How do you distinguish between the convergence arrow and
Yeah.
the supplies arrow?
It's the same arrow. Yes. You have to know. Yes. And the reason is, it turns out there's a lot of other ways to converge. There's almost sure convergence, weak convergence, and this is the convergence in distribution, and there's like a bunch of different arrows. And you're right, this one happens to be the same as the implies arrow, which is sort of annoying, but hopefully you'll figure it out. Okay, great question. So let me give you like one quick example. If you wanted to know what is the mean, this is a very kind of simple example. If you want to know what is the mean of a 100-sided dice, you would say that's approximately, okay, let's make it harder. Let's make the mean of a 100-sided dice cubed. You roll a 100-sided dice, you cube it. On average, how big is that? Well, a 100-sided dice is approximately n times a uniform cubed. Okay? And n times a uniform cubed, I'm going to bring out the n cubed and then do the expected value of u cubed. And the expected value of u cubed is not so hard. It's 3/4. And you'll learn why it's 3/4 in some later course. Or is it 4/5? It's 4/5. Okay. 3, 4. Whatever. It's some number. Let me stop there. So this is, you don't have to know this. I'm trying to explain to you why this convergence stuff is useful. And this is like the most baby version. As you learn more and more of this convergence, you will get more and more powers. And culminating in the central limit theorem, which we'll do sometime next week. Okay, questions or comments about this idea? First of all, this is really bothering me. It's not 3/4, it's 1/4. And it's not 1/4, it's 1/3. Integral of x. It's 1/4. Okay, great. Okay, 1/4. For those of you that know calculus, you got to do the integral of x cubed, and it's 1/4. Okay. If you don't know calculus, shut your eyes and hide. Okay. Next question. We have another one of these. Not the uniform random variable, but same kind of idea, same dice as before. This is a different xn. Don't get mixed up with the xn we just did. Let xn be the number of dice rolls needed on your n-sided dice until you see the first 1. So you roll the dice over and over and over again until you see a 1. Xn is a blank variable with parameters blank. This is like good. This could have been a midterm question. What kind of variable is it? Waiting for the first 1 to appear. I'll give you 1 minute to tell me what it is. All right, 5 seconds left. Give me your best guesses. I think you can enter anything you want here. So if you really don't know, put in your I don't knows. All right, let me take a look. What do you guys think? Again, this is a bread and butter question about the types of variables we learned before the midterm. Let's see what you said. A blank variable. 22 people said geometric. 9 people said geometric random. That's very nice. You corrected my my random. When you do enough random variables, then you don't need to say the word random anymore. Some people said just random. That's horrible. Okay. Of course, it's like technically correct. That's why I'm so mad. Okay. What is the right answer? The right answer is geometric. Very good. So most people, or that was the most common answer. Just over half the people. What else did people say? Yeah. Okay. Great. So it's a geometric random variable, and the parameter is 1 over n. That's the p-value is equal to 1 over n. And why is it 1 over n? It's the chance of rolling a 1 every time you roll. So new problem. New problem. Roll until first 1. And each time you roll, you have a 1 over n chance of succeeding. Each time is a 1 over n chance of success. And therefore, this is geometric with parameter p equals 1 over n. Have the number of dice rolls you need. It's a geometric. And we can play the same game, just like we were saying, what's the value on the dice? We can play the same game with this guy. Here it is in a different Desmos document, but exactly the same stuff. So I have these blobs. These blobs represent the chances of having 1 dice roll or 2 dice rolls or 3 dice rolls. You see, as they get bigger, they go down. So you're most likely to do it on your first dice roll. If you don't do it on the first one, then you're most likely to do it on the second, and so on. This is a geometric random variable. Here the parameter is a half, but if you change n, then you change the values. And in that blue line, I have the cumulative distribution function, which is a staircase. And as you increase n, the same thing happens. It effervesces into nothingness. All these probabilities individually go to 0. Every single probability here goes to 0. You might say this whole random variable just like vanishes. It goes to infinity. The number of dice rolls you need until you roll an n-sided dice and get a 1 is getting bigger and bigger. The more sides, the more rolls you need. This is a nightmare. You're going to be there forever. How are we going to fix it? Same trick as before. So let's call this xn. Why do I call it w? Oh, I'll call it g for geometric. Oh, now I remember. I wanted to call it gn in the mathematized, but I thought that would give it away. So this is gn. So problem, gn disappears to infinity, just like before. Disappears to infinity. That's like dn. The value of a single dice roll, or the number of dice rolls until the first one, they both kind of vanish up to infinity. Fix, solution. What about gn divided by n? So this is like if you roll a 100-sided dice, I measure how long it took until the first one came up in units of 100. How many trials of size 100 did you do? If it's a 1,000-sided dice, then how many trials of size 1,000 did you do? So the bigger the dice is, the more like lenient I am in giving you more room to work with by dividing by n. And this, before, that constrained the random variable to be between 0 and 1, and we got a uniform. But a geometric can be any size. So does dividing by n help? Does that even constrain it at all? Let's figure it out. Let's see what we got to do. Okay, hopefully I have this plotted. Okay, plotted gn. Let's turn this off. So this was the original g. Let me show you the next g, which is them smooshed together. So let's just look at those values. Okay. So let's just look at those values. So the blue are the original values, 1, 2, 3, 4. And then the purple is the blue smooshed by a factor of n. So I take all the values, I divide them by n, and that smooshes them in towards the x-axis. And the blue values kind of effervesce into nothingness. But what do the purple values do? As you add more and more, they kind of clump together, and you get a nice clump of stuff. So every individual point is going to 0, but maybe their clumped accumulation is doing something. And indeed, the way you can tell is to look at the cumulative distribution function. So let's do that. So let me back this up. Let's turn off these blue points. Let's be only purple. Actually, hold on. Let's put the blues back on. Where's my blue? Here. Okay. Here's the blue CDF. Here is the purple CDF. That's green. Okay. Let's make it green then. Everything's green. Let's make everything purple. Purple. Okay. There's the purple cumulative distribution function. And what is the purple cumulative distribution function? It's exactly the blue one, but smooshed. So it's still a step function, but the steps are size 1 over n instead of being size 1, and they're smooshed in towards 0. So I just took the random variable. When you divide it by n, you're smooshing all the values to be smaller. Okay. And now we can ask, does this get closer to something? So as n gets bigger and bigger, what happens to this thing? Let's animate it. So here I'm increasing n, and you can see the little steps are getting smaller and smaller, and the whole function is settling down to some nice looking smooth function. Actually, interestingly, the function looks like something cool. Of course, it doesn't make any sense for these negative values, but it looks like something cool over there. That might help you recognize this function. Does anyone recognize this function from your high school nightmares? When you learned functions in high school, what does this one look like? Yeah. The ln function. Yeah, very good. The ln function goes off to infinity. So this one settles down at 0. Let me flip this function upside down, and then maybe you'll recognize it. So what is this guy called? This guy's called g. Let me make a new guy called 1 minus g. That's 1 minus g. So same function, but I flipped it upside down. This one was getting close to 1. This 1 minus function is getting close to 0. And this one you might recognize. It starts at 1, and then it kind of smoothly goes down. Yeah.
Exponential decay.
It's exponential decay, and not only is it exponential decay, so far we have not seen E anywhere in the course. The nasty E from calculus has not sullied our nice statistics land until today. Not only is it an exponential, it is the exponential. It is the function e to the minus x. That's exactly the exponential function. So this limiting process of adding more and more sides is makes the e appear. We started out with n's and 1's and counting dice, and this e equals 2.77, Euler's e, magically appears as the cumulative distribution function. So maybe I'll focus on just that result. I'll write this down. So fact, gn over n, fat arrow, converges in distribution to something called an exponential random variable. And an exponential random variable has the CDF, f, let's call it f sub e of x, is the function 1 minus x. This e. E is less than x is 1 minus e to the minus x. And it really is the e from calculus class that has magically appeared. Next week, we're going to do more of these, and we're going to do them for binomials. So next week, we're going to do these ones, where we're going to see that the binomial also converges to some nice pictures. So where's my nice picture? Here's my binomial approximation. Okay, see you guys next week. Have a good weekend.